Hello, and welcome to the section Building a Camera App with Panorama, HDR, and AR features. In this section, we'll be learning about various advanced image processing techniques with multiple images. Like, we'll be seeing how we can perform image stitching to stitch overlapping snaps of landscape images. We'll next learn how to generate a montage of video captured from a drone. Then, we'll be seeing how we can achieve a marker-based augmented reality application, followed by trying a markerless approach to augmented reality. We'll then explore how we can capture HDR or higher dynamic range images using OpenCV, and finally, we'll be building an Android application that can generate panoramas as well as capture images in HDR with some AR capabilities. Let's quickly get started building these applications. In this video, we'll learn how you can stitch multiple images to get a single big image, leading to a much wider field of view, also known as panoramas. Now let's have a glance on what you're going to learn. First, we'll see what are the different types of panoramas, followed by a generic algorithm which is very useful for building an image stitching pipeline. Next, we'll have an overview of the architecture of the panorama generator and see the various stages involved. Next, we'll be seeing how we can align the group of images globally and consistently with the minimum error possible in the stitching process. We'll also see what are the different methods to achieve global registration of the images in the panorama. And finally, we'll see a working example of an image stitching engine that we'll use to create the panorama of a scene. Here are some facts on field of views. On average, the field of view of a compact camera is about 50 by 35 degrees, whereas that of a human is about 200 by 135 degrees. We are interested in building an image of the scene at hand that has a field of view of 360 by 180 degrees. Based on the degree of freedom of the camera, a panorama can be of different types, like a 1D panorama in which there is not much effort and we simply achieve a 1D panorama by ordering the images in their respective orders. Whereas in case of a 2D panorama, we still need some extra work to be done, which we shall see next. Now let's have a look at a generic algorithm for building an image stitching engine. Here is the algorithm on which we'll base our image stitching pipeline. As an input, we'll take n ordered images. Next, for each image in the original dataset, we'll select m candidates that has the best match to the chosen image. And then we'll be finding geometrically consistent feature matches using ransack to solve for homography. We may also choose to verify the consistency of the homography operation by using a probabilistic model. Next, we are left with finding the connected components for the image matches. And for every connected component that we get, we perform bundle adjustment to solve the rotation and focal length issues, and finally render the panorama by blending the images. Now that we have seen a generic algorithm behind building an image stitching pipeline, let's have a glance at the system perspective of the problem. As a first step, we'll find corresponding features between frames, and then we'll be performing image registration by overlapping gradient projection and determining the translation or rotation, which is the homography step. And after performing bundle adjustments for better results, we finally blend the images. Let's see an example in Notebook in which we retrieved SIFT features across successive frames. We'll now see how we find the features in images and match. For this example, we'll be using the surf feature descriptor for finding the features in images. We have defined a class called matchers where we create an object of the surf descriptor by using surf create function, and we also initialize the index and the search parameters for the flan based matcher, for which we again create an instance as part of the initialization of the matchers object. Next, we have a function called match which takes two images as input and retrieves their surf features, followed by performing flan-based matching. That way, matches has all the matched points between the two images. And we'll be performing a thresholding on these matches because that will give us a good estimate of the homography between the two images. Good stores all the good matches between the two images. Since homography requires that we need at least 4 points, we enforce this condition and we use the function find homography, which takes the current matched points with the matched previous points to get the homography matrix, which finds the correspondence between feature points in images. Next, let's see how we can achieve global registration in the image stitching pipeline. The goal is to find a globally consistent set of alignment parameters that minimize the misregistration between all pair of images. One way to register a large number of images is to add new images to the panorama one at a time incrementally, aligning the most recent image with the previous ones already in the collection. The process of simultaneously adjusting post parameters for a large collection of overlapping images is called bundle adjustment. In the case of 360-degree panoramas, accumulated error may lead to the presence of gap between two ends of the panorama, which is fixed by a process called gap closing by stretching the alignment of all images. And finally, we need to discover images that go together, which is also known as panorama recognition. Let's see a small example of performing bundle adjustment on a set of images. Now we'll be seeing our image stitching pipeline for generating the panorama. So before stitching, we just show you the sample images. In this case, we use sample images from Adobe, for which you can find the link above. So here's the link for the dataset that we are using for our panorama. And here are the images before we do the stitching. This is a grayscale image of the Golden Gate Bridge, which is a famous bridge over here in San Francisco. And now we'll be seeing the image stitching pipeline that we have created. So we have defined a stitch class. So the constructor of this class takes the input as a file which has the path to the images which will be stitching in that given order. Please note that it's very important that the images are in the order in which the panorama needs to be constructed. So we resize these images followed by defining left and the right list and the center of the images and a matcher object and a prepare list. The next function, prepare list, basically what it does is that given n images, it divides the n images into two separate lists as left images and right images, which works as a divide and conquer based method where we individually stitch images in the left list and the right list, and finally we join the left and the right list to get a panorama. We also have two other functions known as left shift and the right shift, and I'll briefly go over the details of these two functions. As the name says, the left shift operates on the left list that we just created and the right shift operates on the right list. But there is some difference in their functionality. So what the left shift operation does is that per left image it calls the match function that we have previously seen and find the homography between the previous and the current left image, and after we calculate the homography, we calculate the inverse homography, which helps in getting the transformation matrix which we need for doing perspective warping so that we can join the current image with the previous image along the line of the transform so that they get stitched seamlessly. So that way we get the transformation matrix, and dsize gives the estimate of the perspective transformed image which we use as the final argument of the function warp perspective to get a final image which is obtained by stitching the current image so that its orientation matches with the current image. Similar to the left shift, what right shift does is that let's loop through every right list. Instead of doing match operation on the previous and the current right list, we apply a match on the last but one left image. And then we apply homography. We also do a method known as mix and match, which takes the input as the left list and the warped image in the right list, and we perform bundle adjustment and augment the image region that was lost due to the transform by shading it as black and return the warped image. So here are the final calls to the function. First we call the stitch pipeline and then doing left shift and the right shift, and that gives us the panorama. So let's see the output of the following program. So here is the output of the following program, and we obtain a perfectly stitched panorama, which is obtained by stitching 6 of individual images that we have previously seen.